Hi, my name is Sulbei. I'm from Georgia Tech. This presentation is about our journey of building a fuzzing framework for robotic systems. A robotic system is one type of cyber-physical systems that has both hardware and software components. This is an interesting setting because not only the attack surface is larger, but also the interaction between the hardware and software components can lead to complicated issues that never existed in traditional software programs. In addition, such setting makes testing very challenging. We could identify three main challenges. First of all, different robots have different properties. Some require extra precision, some fly, some drive, and so on. We still want our testing methodology to be generic, so we can apply it regardless of the type of the robotic system. Second, the state space is much bigger than any traditional software because robotic systems operate in many different environments and conditions with countless variables existing in the real world. In order to effectively drive the robotic system towards corner cases and bugs, we need to narrow down the state space with a highly effective metric. And lastly, unlike the software systems that are designed to exchange accurate data, physical components are noisy as they interact with the real world. So when designing tests, we need to consider this noisy nature of robots, and that is not trivial. Fortunately, Robot Operating System, or ROS, helps tackling the heterogeneity. In modern robotics, ROS is considered a de facto standard for robot development, and it is adopted by many different parties in the industry, military, and academic institutions. Even the space robots of NASA are powered by ROS. ROS simplifies the robot development. Developers can write nodes that publish data to topics or subscribe to topics to receive published data. For example, if the object detector node publishes data message to topic called objects, all the nodes subscribing to that topic receives the message. In other words, regardless of the type of the robotic system that we're dealing with, the behavior of robots can be summarized as a data flow among the nodes that are distributed over the system. For the second challenge, the input space problem, it's already proven that code coverage guided fuzzing is highly effective in exploring huge input space of a program. Fuzzers have discovered millions of bugs by associating the execution states with code coverage to quantify the usefulness of test inputs. However, code coverage feedback is not almighty. It is effective against general software programs, which tend to have diverse code path and corresponding control flow. However, robotic systems are composed of small distributed nodes that exchange data for state transitions. So not like those sequential programs, their control flow is not that diverse. We have observed that the robotic systems tend to exhibit a wide range of different behaviors, even when the code coverage is the same. In other words, in our context, code coverage-based feedback is no longer effective in providing meaningful insight of the quality of the generated inputs. So fundamentally, how do we determine if the robot is approaching an undesirable state? This is where the semantic feedback comes into the picture. There are certain signs in the runtime that potentially indicate that the robotic system is gradually transitioning into buggy states. Let me introduce an interesting case of redundant sensor inconsistency. The intuition here is that the same type of sensors are expected to report consistent data. However, in practice, the accuracy and the resiliency to errors are different among the sensors due to different manufacturing processes and many other reasons. For example, the flight controller of PX4 drones have two IMUs, inertial measurement units. One is manufactured by TDK and the other is manufactured by Bosch. These two IMUs report consistent acceleration readings when flying under normal circumstances. However, when there's a sudden change of movement, such as a collision, the two IMUs report very different acceleration values because one IMU is much more sensitive to sudden changes of acceleration. We can utilize this characteristic as feedback in our testing by marking the inputs interesting if they lead to bigger inconsistency. Now for the last challenge of noises, it's apparent that we cannot have the perfect model of the physical world, and therefore cyber-physical discrepancy will always exist to some extent. So we decided to rather use this discrepancy to our advantage. In particular, by synchronously executing a robotic system in a simulator and in the real world simultaneously, we can capture the robotic states from both worlds. This serves two important roles. First is filling the gap between low-fidelity simulators and profound physical environments. For example, the notion of power consumption or temperature is usually missing in a simulator, but these are the states that are closely related to the safety and reliability issues. Second, we're looking for divergent states. If two robots end up at different locations after receiving an identical set of messages, that tells us that there were substantial amount of noise that intervened the operation of the physical robot. So like shown in the figures, we created nearly identical environment as the physical world in the simulator and execute the robot in both of them, trying to see states from both worlds. This way, the noise provides us with rich information of the discrepancies. Now that we have a clear idea on how to tackle the challenges of testing robotic systems, let me define the bugs. In this project, we focused on a new type of bugs that are unique in the robotic context, and we refer to the bugs as correctness bugs. These bugs are interesting because they do not really have immediate manifestations like the classic software bugs, but they may have potentially more devastating impacts. For example, let's imagine that the hardware of a space robot quickly wears out due to a specification violation, which keeps pushing the robot beyond its physical capability. That will cause big problems. Specifically, we could define 3 types of correctness bugs, where robots do not conform with the laws of physics, do not stick to the specification, and where the simulated robots behave differently from the actual robots. Putting all the pieces together, we built a fuzzing framework called RoboFuzz. It's a customizable, semantic feedback-driven fuzzing framework tailored for ROS internals and ROS applications. The architecture of RoboFuzz is similar to that of a typical feedback-driven fuzzer like the AFL, except a few ROS-specific components. The system inspector examines the robotic system under test to extract a graph which consists of all nodes and topics of the robot. With this information, RoboFuzz can select the topic to inject messages and test specific nodes that receive the messages from that topic. The message mutator is capable of doing structure-aware mutations by selectively mutating the values in the fields without destroying the structure of the ROS messages. Then, as I mentioned before, we run tests on a hybrid execution model utilizing both simulated and physical robots. RoboFuzz configures a virtual robot and an actual robot to subscribe to the same topics, and then publish mutated messages to these topics so that both robots can receive the identical messages and take corresponding actions. This allows RoboFuzz to capture states and events from the simulation and the real world at the same time. Next up is the oracle handler, which collects and merges states from the hybrid execution. It checks whether the merged execution states conform to the correctness oracles or not, and reports if any violation is found. Since the notion of correctness is different across each robotic system, we provide oracle templates to allow developers to conveniently declare the oracles of their own systems. And we also define several correctness oracles for the robotic system that we tested, and the details are available in the paper. Now, the last component of RoboFuzz is the feedback engine. This engine engages when no bug is found by the oracle handler, and it calculates the feedback score using the semantic feedback matrix I mentioned earlier. Like the traditional fuzzers, messages with higher feedback scores are considered interesting, and they're in-queued to get more mutations in the subsequent cycles. With the prototype implementation of RoboFuzz, we tested 6 target systems. 2 of these are the internal layers of ROS2, including the type system and the client library implementation, and 4 are ROS2-based robots with different properties. As a result of fuzzing each target for 12 hours, RoboFuzz revealed 30 new correctness bugs, out of which 25 are acknowledged and 6 have already been fixed. 13 of these were found in the internal layers, meaning that any robotic system built based on ROS are affected. Among the applications, we utilize hybrid fuzzing for a PX4 drone and a turtlebot to showcase the use case. Let me demonstrate a simple bug that clearly shows how a specification violation is manifested as a cyber-physical discrepancy. In this video, turtlebot is hooked up with the hybrid executor. When the fuzzer sends a velocity command, both robots should react the same way. When a command to move at 0.04 meters per second is issued, both robots follow the command and move at the set speed. However, there's a bug in the implementation of the motor driver due to imprecise floating point value calculation. So because of this bug, even though the documented maximum linear maximum linear velocity is 0.22 meters per second, the physical robot fails to execute the command to move at the maximum speed. On the other hand, in the simulator, the command is accepted and executed because the simulated model does not rely on this faulty, defective motor driver to move. RoboFuzz captures this cyber-physical discrepancy and reports the bug. To evaluate the effectiveness of our semantic feedback mechanism, we tested the PX4 drone, once with and once without the semantic feedback guidance. With the guidance of semantic feedback, RoboFuzz found 9 buggy cases, but without the feedback, it only discovered 2 bugs in 12 hours. Here, if you take a closer look at the individual feedback scores until reaching each buggy case, we can observe that there's an upward tendency of the score before a bug gets to be triggered. This means that by prioritizing the mutation of the inputs that increase the semantic feedback score, we could trigger more bugs more efficiently. In summary, we targeted unique correctness bugs existing in ROS and ROS-based robots by using semantic feedbacks and hybrid execution. As a result, we found 30 new bugs in 6 different systems. We've open-sourced RoboFuzz with supplementary materials at the URL, and the artifact was evaluated and received all 3 badges. This is the end of my presentation. Thank you.